Alright, I'm going to pick up where I left off in the previous video. We're working on part number 4. We're trying to find the rate at which the volume of water in the pool is increasing. That's dV dt at t equals 8. And we're also trying to find out how fast the water level is rising. That's dH dt at t equals 8. So we started with the volume formula, which is V equals pi r square h. Because r is a constant of 12, we can simplify that to be 144 pi h. We take the derivative of both sides with respect to t, and we get dV dt is 144 pi dH dt. Then we do know that the volume of water in the pool is defined by an integral defined function, which is 1000 plus integral from 0 to t of p of x minus r of x dx, and the derivative of that, dv dt, is just p of t minus r of t. And dv dt when t is equal to 8 is just p of 8 minus r of 8, which we plug in 60 from the table above, r of 8, which we plugged into our calculator based on the function we have. So you recall that since we have y1 equal to 25e to the negative 0.05x, which is our r of t, then we can simply go to the home screen, vars, yvars, function, y1, and put in parentheses 8, and that gives us 16.758. Then we can do 60 minus that answer, and we ended up with 43.242. So that's dV dt at time t equals 8. Alright, so I'm going to plug that back into our formula. Let me get rid of the calculator here. So I plug in 43.242 for dV dt. And at this point, all I need to do is divide that by 144 pi, and I'll end up with dH dt. And so I take the 43.242, I divide that by, I have to use parentheses here, 144 pi, and I end up with 0.096. Okay, and then we need to discuss the units of both of those answers. So dV dt at time t equals 8 is 43.242, and that is going to be rate of change of volume with respect to time, so that's going to be cubic feet per hour. And then for dH dt, height is a linear quantity, so that's feet. So that's going to be 0.096 feet per hour. And that brings us to the end of this problem.